Yes, Chinma, I can see you. Chinma.
Chinmay sir, in fact,
Muted Chinma.
oh, sir, are you there, sir? Chinmay sir?
Yes, I am there. Am I audible? Am I audible?
Yes, yes.
Yeah. Good evening, good afternoon, everybody. Jawad sir and of course Professor Segbe. I don't know. I don't see his video from my system. Hello, Professor Segbe.
Yes.
Yeah. So thank you very much for accepting the invitation of Kerala APS and this student branch of GC Barton Hill. We are really pleased and it's a real privilege to have you.
Thank you very much for inviting me.
Yeah, right. So I hope you have visited India quite a few times. You are there in last INCAP, right?
Not last one, before that one. In
Hyderabad.
Yes, Hyderabad, yes.
Okay, yeah. 2018.
2018, right. December 2018. So maybe
Yeah.
next year I'll visit one more time.
Right. This one anyway is going to happen in virtual mode. Probably not in a full-fledged fashion.
I see, yeah. I would love to be there one more time.
Right. How are you doing?
I'm fine, and you?
Yeah, we are fine too, amidst the challenges that all of us are facing. And we are really pleased to have Professor Siddiqui. He had a long travel. He was there in Kingston with Professor Antar for a year almost. And then I guess just 48 hours before he landed in India.
Okay. It's good to see him.
Yeah. So have we tested your audio and your screen sharing part?
Yes, sir. Yes, sir. Sir has done that, sir.
Okay, thank you very much. In fact, I was a bit late to log in. Yeah. Sir, you are muted, Professor Siddiqui. You are muted. You are telling something, I guess.
Yes. Yeah, we were planning to have you here in Kolkata. You remember we had talked in Egypt that somehow, like things have changed so much. Hopefully, have more physical, probably a year later after the vaccine is out, hoping on that. So how are things in Turkey?
Turkey is doing fine, not too bad.
Yeah, I think Canada was doing fantastic. They have everything under control. Everything under control.
Because probably Canada, in normal situation, also Canada maintains social distancing.
Yes, things are more disciplined and more, people follow the rules. And of course, population density is pretty low. So that is an advantage.
Yeah.
I guess it is 3/400.
Yes. Either.
3 parts per kilometer for Canada and for 400 in India.
Yeah, exactly. It's three per square kilometer, and it's 300 in India.
Yeah, now it is 400 actually. 300 is little bit, probably a couple of years before or so. Yeah.
I can see Dr. Devdeep Sarkar has joined in.
Yeah,
Good evening.
we have Dr. Devdeep.
Yeah, good evening, Professor Sevgi. Good evening, Dr. Shaha. Good evening, Jawad sir.
Yeah.
So I guess it's almost time, right? I joined little
We
late.
have another 4 to 5 minutes.
4 to
We'll
5.
go as per the schedule.
Okay.
And just to update Professor Segbe, before we come formally, this part of India, like southern part of India, even though we started a lot of activities when I was in Kolkata under Professor Guha, Professor Siddiqui, of course. But now we are really vibrant. These student branches, we have 5 student branches in Kerala, and all of them are equally vibrant. And recently they conducted all Kerala APS student conclave. In the same state, we have 5 APS student branches along with the full branch. And that in that student conclave, Professor Yahya was there to inaugurate the event. And we had good talks, very good focused panel discussions. This particular college, which is being mentored by Professor Anu Muhammad, they are extremely vibrant. They are extremely vibrant, and they are actually the resources for us. They do all the background work for conferences, workshops, and they do a lot of type of events for industry visits, sometimes ISRO center visits, space industry visits, so on and so forth. We are really pleased to have you also. Thank you. Yeah. Professor Siddiqui, Dr. Sharkar, they have visited here in different capacities during different conferences and some workshops, stuff like that.
That's good.
Yeah, so we'll have try to have a physical visit with you here as a proper DL in future. I believe last year also Dr. Rao was here as DL speaker in December. After INCAP, he came here.
I know. Yeah.
Yeah, every year at least we get one DL talk along with other part of India. Yeah.
That's great.
So we are a couple of minutes we have. So Shapnil, you may say a few things. Anu, you are there?
Yes, sir. Can just wait for the host to start with the proceeding.
Yes.
Meher or Malvika, are you here?
Can we start?
Yes, we can start.
Am I audible?
Yes, you're audible. You're audible.
So, good evening, everyone. We have all gathered here this wonderful evening to experience the technical edge of electromagnetic engineering with a distinguished lecture program conducted by IEEE APS Student Branch Chapter of Government Engineering College, Barton Hill, in association with IEEE MTTS Kerala section. I am Meher from GEC Barton Hill.
And I am Malavika from Government Engineering College, Barton Hill. Today we have with us Professor Dr. Levent Sevgi, IEEE Distinguished Lecturer, to widen our knowledge on the topic from engineering electromagnetics to electromagnetic engineering, teaching and training the next generation. And now we would like to invite Mr. Swapnil Sinha, Chairman, IEEE APS SBC GECBH, to give us a brief idea about this DL.
Okay, hope I am audible.
Yes.
Yes, you are. Shapnil, go ahead.
Okay, sir. Good evening. Namaskar. Welcome to the first lecture of APSDL at Government Engineering College, Barton Hill, in association with IEEE Kerala Chapter MDTS and in association with our L4 series. L4 series. I extend my warm welcome to Dr. Levent Sevgi, the speaker of the day. It's a great privilege and honor to have you with us, sir. We are very grateful to you to have accepted our invitation beside your busy schedule. I welcome you, sir.
Thank you very much. Thank you.
I would also like to welcome Dr. Chinmoy Saha, former APS chair and present MDTS Kerala section chair, who has been a constant source of support and guiding beacon through the years since we have started. I welcome you, sir.
Thank you.
Now I would like to invite Professor Anu Mohammed, Chapter Advisor APS FDTS GECB to this event. He has been a constant source of support to us and always been available to us with any doubts regarding this for the events or anything else. I would like to welcome Professor Anu Mohammed, sir.
Hi, Swapnil. Hi, Swapnil.
As we know, IEEE Antennas and Propagation Society thrives for advancement of theory and practice of electrical and electronics engineering. IEEE APS GECB Student Branch Chapter Kerala section is active since February 2019 and has been conducting numerous talks and workshops and conclave on various content regarding the antennas and its application. Unlike the normal talk sessions, today we bring you IEEE APS Distinguished Lecture Program, brings you experts around the world to give lectures on topic importance of interest and importance of antenna and propagation society. Today we are very fortunate to have Dr. Levent Sevgi, professor at Istanbul OKAN University, Turkey, Department of Electrical and Electronics Engineering, to provide the distinguished lecture on from engineering electromagnetics to electromagnetic engineering. He is an associate editor of IEEE's Antenna and Propagation magazine, the writer and editor of the Testing Ourselves column since 2007. He has been involved with complex electromagnetic problems and systems for more than 3 decades. I would like to take this opportunity to thank our Vice Chair, Mr. Sahadar Sharif, who took the lead for conducting this event and dealt with all the proceedings which were recorded for this event. Due to connectivity issues, he is not able to talk with us right now. So I would also like to thank him for all his work which he has done towards this APS deal. And that's all. I welcome you all to this event. I hope we have a great session. Sir, welcoming you. Thank you.
And now, as a formality, on behalf of IEEE APS and MTTS GEC Barton Hill and MTTS Kerala initiative, learn from leaders, learn from legends, we are delighted to welcome you, sir. In fact, I came to know you through my professor, Rishida sir, while we were talking on full wave analysis, somewhere on full wave analysis. Then he was mentioning about this physical theory of diffraction by Ufimsev. And when I went through that book, it was the first time I am seeing your name, sir. And that was the first time I came to know that so and so a professor is there at Istanbul. And I'm very happy that you associate with Ufimsev and all that's about in physical theory of diffraction and all. We welcome you, sir, and I am happy that and appreciate my students for sensibly choosing this topic for the DL program. And I welcome all the faculties and industrialists associated with various institutions, organizations across the globe, and also students from all over the world. We are very happy with the way students responded and have decided to attend this talk. My suggestion is to them is that to get involved with this AP and MTT societies, especially undergraduates studying in communication engineering. Believe me, you will be technically benefited. As mentioned earlier, I appreciate my students for sensibly choosing this topic for our DL program. Our societies, AP, MTT, GEC, Barton Hill, always associate with Indian Institute of Space Science and Technology, and I express my sincere thanks to Dr. Chinmay Saha, with whose support and motivation the formation of both chapters happened at GEC Barton Hill. Thanks a lot, sir, and we got benefited through you. And the platform you gave to our students, and expecting more support and mentorship from you, sir. And definitely, I feel that the students will be able to technically contribute back to IEEE. Also, I use this occasion to express sincere gratitude to Mr. Arjit Mitra, scientist Vikram Sarabhai Space Center India Space Research Organization, for being a valuable mentor and asset for our students. Unlike with the case of other societies, the RF domain our AP MTT is working on You definitely require these kind of webinars to know the physics behind, and if you have a grip with the coding techniques, then you will be the one which will be most sought from the industrial perspective. In essence, let us learn from Sevgi sir, and hoping to hear from our speaker of DL about the 4 Maxwell equations and boundary conditions. If understood properly, then rest are just mere applications in field theory. With this, I hand over the virtual podium before Levent Sevgi sir speak to Dr. Chinmay Saha sir. Dr. Chinmay Saha.
Thank you, Professor Anu. First of all, I am really sorry to stand between the speaker and the audience and taking few minutes. Yeah, I can't refrain myself also to take this opportunity to update Professor Segbe regarding the activities this APS Kerala and this especially the Government Engineering College Barton Hill and MTTS Kerala chapter has initiated during the pandemic. We all know that interglobalization is facing a very difficult time, and like other part of the globe, India started going in lockdown around mid-March. So during that time, this APS Kerala and MTTS Kerala together first came up with this webinar initiative in India, and that was a huge response, overwhelming response with almost 600 participants from different part of India and abroad also. And it was so overwhelming and motivating for us, the free platform like Google Meet or others having some limitation of in terms of participation and the timing, we had to go for having our own platform. So we combinedly came up with this WebEx platform, which is a purchase version by us. So I just mentioned this point to indicate the response, the activities that we are having. So firstly, I once again welcome Professor Segbe and sincere thanks on behalf of all the members and on behalf of all my colleagues of the chapters, APS as well as MTTS Kerala. And as a matter of information, I just want to mention that during 2018-19 IO, when I was the chair of APS Kerala, we took an initiative that the activities should spread not only geographically, also to the different kind of students. Normally, the IEEE DLs and IEEE talks that we hear during conferences and workshops, sometimes those are a little bit high end, and for UG students especially, those are not always very easy to digest and easy to understand. So with this kind of motivation and a lot of requests from some of the local faculty members, we came up with some kind of events which are obviously above the class level, regular class level, but also little bit below the IEEE DL level, so that they get the actual meaning of IEEE benefits also, because I can't just tell my students that you join APS and MTTS as a member and you will be benefited, because there should be real and tangible benefits in getting associated. So with this kind of idea, within a couple of years or so, we came up with 5 student branches and different parts of Kerala. And it is a really, matter of great pride to see me that the saplings that are embedded at that time are really now big trees, and they are organizing talks like IEEE DL talk. Of course, our thanks to the regional 10 coordinator, Professor Siddiqui, Professor Poddar has always been very supportive to us. As I was mentioning before the event started informally, that very recently we had this All Kerala IPS Student Conclave, and we have initiated a new series which is named as L4, Learn from Leaders and Learn from Legends. The word learn is repeated just to keep a symmetry. This L4 is Professor Segbe. Needless to mention, he is a legend in our field, and he is definitely a leader, IEEE leader in terms of various activities and association. So this talk is a joint talk by IEEE APS DL, also co-hosted by MTTS L4 series. And as I mentioned that this kind of initiative during this COVID enforced lockdown, it is not something that completely thought by us. We just took this initiative, but as you have seen, most of the conferences even the society conferences like APS 2020, IMS 2020, UCAP, most of the conferences have gone virtual. And with the given situation, probably at least for another years or so, we have to have the virtual series, virtual event, all the conferences, and also probably the hybrid mode will be initiated later on. So with this, I again extend my sincere thanks. And before I, introduce the speaker, I will just take another couple of minutes to show some of our activities that mainly is driven by our students. So I share a few slides over here. Just let me know if you can see the screen. Do you see the screen?
Yes. Yes, I see.
Yeah. So I really don't want to take time. Firstly, this is the another feature that I want to mention. All the events the students are organizing, they come up with very beautiful, colorful flyer. And as you can see over here, this talk is jointly organized by APS Distinguished Lecture Program of and GEC Barton Hill, and also IEEE MTTA Scala Section L4 series. Before that, during 2016 and 19, we had various type of activities for students, visits, different kind of workshop, conferences, mini colloquium, and space visits, etc. You can see some of the activities. I mean, these are basically the photographs of inauguration of APS GEC Barton Hill, the today's main host under Professor Anu Muhammad. You can see, and this was another APS student branch that was initiated in 2019, Ahilya School of Engineering, along with that Musiliar College of Engineering that was also initiated in 2019. Well, before that, we have IEEE IIST student branch, APS chapter, and also very recently we have come up with another APS student branch in the form of, Cochin University of Science and Technology. These are some glimpses of our recent activities. Just before the pandemic, we had Dr. Rao with us, along with Dr. Anandan, Dr. Pandey, Dr. Raghavan, Dr. Apren. We had a space antenna workshop. This event is again in pipeline this year, but this year we'll be doing in virtual mode. Maybe a little bit of hybrid we can come up with. So this was jointly organized by MTTA Scala chapter and APS Scala chapter. We always appreciate the efforts of our students, and we we understand and we value their support. So during these events, some of the student volunteers who are always working tirelessly behind the scene are felicitated. During 2019, we had also another mega event which was part of IEEE 10Con, Region 10 conference. APS, GRSS, and MTTS together came up with 10GARS 2019, which was co-located with 10Con. You can see some of the stalwarts in our field. Also, Professor Siddiqui, Dr. Dadwal, Director IIST, inaugurating the event, along with myself and Dr. Naresh was the co-organizer for this particular event. And as Dr. Anu was also mentioning, we encourage a lot of site visits for the students. This was one such program where there was a visit in Cochin University of Science and Technology. They have come up with a radar facility, that ST radar facility. So this is a big array of Yagi antennas, which was attended by various students, and then ham radio and different other kind of webinar activities you can probably see. This was the inauguration of MTTA Scala chapter. Dr. Chattopadhyay from JPL NASA, Professor Shivon Kaul came there along with Professor Siddiqui, Dr. Pandey, and others to inaugurate the event. And interestingly, this particular event was reported in IEEE MTTS magazine. We also conduct different type of workshop even for school students to make them aware of the IEEE and different kind of societies, especially the antenna propagation and microwave theory and technique society. These were some of the events. We came up with a new concept of 3-minute project and thesis competition, which started in 2019. We did 2020 also, and this is going to be an event which will be continuing in the future also, maybe in what this has really got a new directions. So as I was mentioning, L4 series was inaugurated last month by Professor Sunda, Professor Cole, and President himself, Dr. Ala Abudale. And that was followed by 2 talks by Professor Cole and Dr. Nuno Carvalho. And then very recently, we are really fortunate to have Professor Antaru with us for inauguration of this All Kerala APS Student Conclave, which was basically a brainchild of this 5 student chapter chair, and these are the associated faculty advisors of these colleges. And then there we had very good panel members, Professor Siddiqui, Dr. Saptoshi Ghosh, Dr. Devdeep Sarkar. President himself was one of the panel members, and I basically moderated this talk. Very recently, we had L4 talk by Dr. Gautam Chakrabarty, and this one. And probably you can understand as a recognition to our diversified activities, vibrant activities, we got the best APS outstanding chapter award in 2018 when I was the chapter chair and previous chair was Professor Anandan. So it was a joint activities and it was a true recognition, and we really look forward to many such recognition and many such activities. So with this I conclude my presentation, and with this announcement that this is a future event in upcoming weekend. We will have Professor Asunda Henderson and Professor Ramesh Gupta with us to inaugurate, to have this particular event over here. Now, with this, it's my great pleasure to invite Professor Segbe to start his talk. But before that, let me take a minute to introduce him. Professor Levent Segbe is a fellow of IEEE. He received his BE Engineering, ME Engineering, PhD degrees in Electronics Engineering from Istanbul Technical University in 1982, 1984, and 1990 respectively. In 1980, that allowed him to work with Professor L.B. Felsen at Webner Research Institute, New York Polytechnic University, York for 2 years. His work at the Polytechnic concerned the propagation phenomena in non-homogeneous open and closed waveguides. He was with Istanbul Technical University during 1991 to 1998, TÜBİTAK MRC, Information Technology Research Institute during 1999 to 2000, Webinar Research Institute, NY Polytechnic University from 88 to 1990, Scientific Research Group at Radian System Canada 1998 to 1999, Center for Defense Studies, ITUV SAM 1993 to 1998 and 2000 to 2002 with the University of Massachusetts, USA as a full-time faculty 2012 to 2013, and with DOG-US University 2001 to 2014. Since September 2014, he has been with Istanbul OKAN University. He is having an H index of 32 with a record of more than 3,605 citations. Google Scholar document you can see. I think this is a very humble bio Professor Segbe has sent to us, but I know he's much beyond that, and that's why it's a real pleasure to call this talk not only a DL talk but also a L4 talk, learn from leaders and learn from legends, because we understand that he's a real leader and he's a real legend contributing immensely in this particular field. So with this, I extend this virtual podium to Professor Segbe. Over to you, Professor Segbe. Thank you very much again.
Thank you for this introduction and thank you for the invitation. I appreciate it. And let me share my presentation.
Sir.
Yep.
Can you just speak up? Your voice is low.
Okay. How is the volume now?
Okay, sir.
It's okay. It's fine.
Okay, sir. Yeah. It's fine, sir. That's okay.
Okay.
Sorry.
Slides.
Yes, sir.
Hello?
Yes, sir. Yes, sir. It's visible.
Yes, sir.
Yes, sir. It's visible, sir.
I don't know how to bring it front. Now? Hello?
Yes, sir.
Yes, sir. We can hear you, sir. We can hear you, sir.
Okay, let's start. This presentation is one of my distinguished lecture presentations, and the title is From Engineering Electromagnetics to Electromagnetics Engineering. The next 3 years, including 2020, I will be giving some other lectures also. The second one is guided wave theory, which can be taught as both undergraduate level and graduate level courses. One is about modeling and simulation of electromagnetic wave propagation. 3 are electromagnetic diffraction modeling and simulation, engineering from design to market, and finally, antennas and antenna arrays in beams theory. The outline of today's talk is as follows. I will give you a few slides about engineering first, then move to electromagnetic engineering. I will discuss some fundamental terms and concepts on electromagnetic modeling and simulation, and then discuss software calibration, which is critical in modeling and simulation. I will show you a few examples about tools that we have been sharing with the IEEE Society, which can be used in teaching and training, especially next generation, young people. And the presentation will end up by the conclusions and discussions. Let's start with the engineering. Now, engineers solve problems. Actually, life is problem solving, but the definition of and the solution of the problem differs from discipline to discipline. For example, for a solution, showing the existence and the uniqueness of the solution is the solution. But we are engineers, we deal with observable-based real-life problems under given accuracy. So, of the solution, in addition to the existence and uniqueness, are also important for engineers. Engineers do not seek the best solution, not the cheapest solution, not the fastest solution. Depending on requirements, which mean the budget, the time, the criticalness of the problem, engineers have to seek the optimum solution. We are engineers. We deal with physics, we use mathematics, and we speed up with computers. So this necessitates an internal balance among mathematical background, which means theory, engineering, which means practice, and numerical simulations, which means computer capabilities. We speak with numbers, but can be given only as a result of a measurement or a computation. Therefore, engineers need to well understand the definitions of, for example, sensitivity, precision, and resolution, and the results are not if you don't state the error, the uncertainty range, with the confidence limits. Real-life problems are not deterministic, are not stationary, are not linear, and are not homogeneous, but especially for the undergraduate and in many engineering problems, we assume they are. For example, suppose you repeat a measurement n times with a quantity, let's say x, then the mean average value of x0 will be given by this equation. The error or the standard deviation will be given shown on the slide. So you need to well understand the mean, the standard deviation in multiple measurements. If you give a number which is after a computation, or try this with a given confidence limit, let's say for example 90% confidence limit or 95% confidence limit, the measured computed value is x0 plus minus delta x, such as for example 1 plus minus 2 meters to measure the distance, which means all I can say is x is between 121 and 125. So there is an uncertainty range. Within that range, engineers nothing about the result, but the engineer states that x cannot be beyond this range. Theoretical and measured electric field in the videos on the slide. So here are some fundamental questions. Do a measurement. Who will do the test and measurements? In which environment will and measurements be performed? What type of equipment will be used to bring and measurements? Who will monitor or control the test and measurements? Who will control and authorize everything, the process? How will you be sure that everything is okay or under control during these processes? How will you control systematic and random errors? How will you present the results? But these are some critical questions that should be answered before the measurement. Keywords in measurements are authorization, accreditation, calibration, and certification. We do computations, calculations. But remember, physics is a subset of mathematics, which are also subset of the discrete world. So the most general one is the discrete world. So a mathematical solution is your physical solution, and a discrete solution may not be your mathematical solution. So it is the engineer's task to seek the physical solution in the discrete environment. So you have to get rid of non-physical solutions. The frequency of a sine signal, which is a singleton signal, is f0, as shown in on this slide. So mathematical Fourier transform gives signals at plus and minus f0. So we have negative frequencies, which are not physical, but mathematically there are negative frequencies. And discrete Fourier transform gives infinite number of multiples of f0. You have to be careful about choosing the right signal, the physical signal, the meaningful signal among infinite number of non-physical signals. Fast Fourier transform gives signals at negative frequencies. So here are the DFT or FFT challenges: discretization, numerical integration, and finite time duration. These challenges all introduce non-physical results. The resolution and maximum frequency depends on the record time in the time domain and the sampling rate in the time domain. For example, suppose you have 4 different tones, F1, F2, 3, and F4. And suppose maximum frequency and the frequency resolution is as given on the slide in the grayscale area. In this gray area, only F1 appears at its right frequency, but the other 3 will appear as ghost signals. So F1 is physical signal, but F2, F3, and F4, they appear as ghost signals in your frequency range. So you have to be very careful when dealing in the discrete domain. These are all ghost signals. Signal report and sampling rate are not properly chosen. Only one of 4 tones appear its frequencies. The rest are ghost signals. Now let's see a few slides about electromagnetic engineering. All of waves has been increasing. We have been surrounded by electromagnetic waves everywhere. We have communication systems, remote sensing systems, integrated command control, surveillance systems, transportation systems, marketing, and these are only a few areas where electromagnetic fields have critical importance. Most of these systems frequencies in the frequency range from DC 0 Hz to terahertz, and the sizes vary from nanometer scale to kilometers wide. Almost all of these systems are broadband today and digital, so they have to operate close to each other, and they result in electromagnetic interference problems. Therefore, we have witnessed the transformation from engineering electromagnetics to electromagnetic engineering for the last few years. So instead of calling microwave engineering, radar engineering, biomedical engineering, antenna, propagation, communication, we prefer to call electromagnetic engineering. Here you see some research areas under. We have propagation problems, microwave circuits, technology, scattering and diffraction theory, antenna design, EMC problems, wireless communication, 4G, 5G, 6G, new materials. We have remote sensing, subsurface tomography, and multi-sensor integrated systems and biomedical engineering. To deal with all those problems, all those research areas, we are lucky because we have well-established electromagnetic theory. We have Maxwell's equations, either in differential form, as you see here, or in integral form. And electronic engineers or electromagnetic engineers use 2 different theories, electromagnetic theory and circuit theory. Circuit is a subset of electromagnetic theory. So actually we all have electromagnetic theory, which is well established by Maxwell's equations. New generations, young people, may find these equations unattractive because we have triple integrations, double integration, second order different equations. But all we need is to differentiate, which is nothing but subtraction, or integrate, which is nothing but addition of electric and magnetic fields in time and in space. So we have Maxwell's equation. It gives you general solutions. Once you state your boundary conditions, now it gives you only your solution which belongs to that. So Maxwell equations plus boundary conditions gives you your solution. Solution is unique, and then if the solution is observable, then you can find the result. We have analytical exact solutions either in integral form or in series summation, infinite summation form, but they exists only a limited number of highly idealized problems or highly idealized geometries. Therefore, we have analytical approximate solutions, which we call high-frequency asymptotics. And for the last few decades, because of the fast growth in the computer memory and speed, we have numerical solutions. But we still have discretization, memory, and time, computation time problems. Usually, we can group electromagnetic problems into three: radiation problems, antenna and radiation problems. You start with Maxwell's equations and boundary conditions. Then you define and use auxiliary scalar and vector potential functions, and then derive electric and magnetic fields. So if you have an antenna radiation problem, it's better to use vector and scalar potential functions and then derive electric and magnetic fields. The second group is and radar cross-section. So again, we start with Maxwell's state our boundary conditions. Then we represent total fields in terms of incident plus fields, because we always know the incident field. It's our signal that we send to the object or to the target. So we send an incident field onto the object, satisfy the boundary condition, get the electromagnetic field target or object interaction, and then calculate the scattered fields. The last one is guided wave propagation problems. Again, we start with Maxwell's equations and state equations. Then we apply transverse and longitudinal decomposition because we have a propagation direction. So, direction we have Green's function problem, and in the transverse domain we have two problems. So these are discrete observables. Observable means computable or measurable. We have rays, low rays, physical optic rays, and then diffraction, GTB, UTB, and PTB, or guided wave problems, normal modes, adiabatic modes, and intrinsic modes. We have beams, complex force points, pulse beam, and parabolic creation methods. Since none of these methods or can give you general solutions, hybridization or hybridization these solutions with observables is a clever way to deal with electromagnetic problems. So you can combine rays and modes together. You can combine mode and parabolic creation, and you can combine geometric optic rays with parabolic creation. Because of the computer capabilities in the last 2 or 3 decades, we also have time domain observable objects like wavefronts, wave packages, and potentials. So here, as we said before, observable means computable or measurable. Asymptotics, which we call analytical methods, are as shown here. We have GO, GTB, UO, and PIP. And the first three are ray-based models, so you use Snell's law. But the last two are post-induced current-based models. Let's call them physical optics or physical theory of diffraction. And well-known techniques are FTDT, PLM, which are time domain methods, or method of moments, parabolic creation, and finite element, which are frequency domain methods. We also have method of moments. To face an electromagnetic problem, we need to consider the signal strength, time and duration, discontinuities, and economic and boundary conditions. And among these parameters, we take into account time frequency relation when we use frequency transform at EBFT in the discrete environment. We need to take into account frequency and frequency impedance relations. Move on to electromagnetic modeling and simulation and some fundamental terms. So we deal mostly with deterministic problems, especially for undergraduate lectures. And we search roots of nonlinear equations. We usually have systems of equations, and by n unknown and n equations, we solve them. Integration, like radiation integrals. We do differentiation, like, for example, wave equations. We interpolate and extrapolate results because we have finite data. We usually have finite data. But life is so there is randomness, probability, statistics, error, and uncertainty at a given confidence levels. So we have different types of simulation. We have task-trained simulation, virtual reality simulation, mannequin-based simulation, live simulation, and physics-based simulation. What we are discussing in this presentation is this physics simulation, not the others. So the definition of this one is as follows. Physics-based simulation is numerical simulations based on physical understanding and mathematical representation of a real-life problem, device, or system. So we have a model, which is a...
Sir, sorry for interrupting. The voice is kind of feeble, so we request you to kind of, can you increase your voice or something, do some adjustments there?
The volume?
Yes, sir. Like, like some adjustments or headset. I think it's feeble, kind of.
So how is it now? Is it okay?
Yes, sir. Yes, sir. It's okay now.
Okay.
Thank you, sir.
So a model is a physical or mathematical abstraction of a real-world process concept. Simulation concerns with modeling of real-world problems. There is nothing but a program or a series of programs. And here are the questions when you deal with simulations. Why and when do we need simulation? Very often, it is expensive and time-consuming. Sometimes it is dangerous. Sometimes it is impossible to do tests with real systems. And sometimes we don't have the real system. That's why we model and simulation. We try to understand the system with model and simulation first, and then create the system. And finally, we can play what-if type games once you model and simulate your problem. So we have real-world physics, we have mathematics, the conceptual model, and we have computer program. So the real-world problem is unique, but there may be infinite number of mathematical models or conceptual models. We choose one of them, and from that mathematical representation or conceptual model, own computer program. But everybody may write different types of programs, and then you get the results. So within these, we have numerical analysis and parameter optimization modules. And once you finalize it, you can add graphical user interface design capabilities for visualization purposes. And we call this electromagnetic package or electromagnetic virtual tool. So you start with Maxwell's equation, you do discretization, and get your virtual tool. And virtual tools are either in closed form representation or in open form representation. And a closed form representation is method of moments. You have unknowns with n number of equations. So they are stable, but huge matrices are made required. And the construction of the problem, discretization of the problem may be a challenge. For the open form, iterative representation, an example is FTDT, finite. It is conditionally stable but the sizes are small and the construction or discretization are easy. Have your electromagnetic package or virtual tool, you need calibration. So in the following few slides, I'm going to show you how we calibrate a software. So when you build a model, remember you introduce assumptions, you several effects, you do approximations and do simulations. And use a computer, you do discretization. The first four of them belong to another form. The last one is synthetic form. So it's a real challenge to do a job in a discrete environment. So validation, verification, and calibration becomes B and C. The definition of validation is as follows. It asks the question whether the right model is built. On the other hand, verification asks the question whether the model is built right. And calibration is nothing but testing the result against a reference data. But what is the reference? That's the critical question. Analytical exact solutions, they can be used as reference. For example, we have flat earth, perfectly electrically conductor flat earth, and two-ray model. It is used to calibrate, for example, open field test sites. We also half wavelength dipole and horn antennas with mathematical exact representations. Therefore, they are used in antenna calibration. But remember, once you calibrate your open field test site, antenna calibration can be done easily. Just the opposite. If you have calibrated antennas, you can calibrate your open field test site easily. So analytical exact solutions are very valuable, but only limited solutions. You interrelations and terms in electromagnetic modeling and simulation. We have real-world problem. We write a conceptual model, but a set of mathematical equations. So we do conceptual validity physics-based analytical modeling. Then we are sure that this conceptual model is a real-world problem. It can represent a real-world problem. Then we write a computer model, computer code. We do computer programming, and we run the computer and do operational validity through numerical and physical experiments. So if you are an engineer, this way or that way, at the end, you must do a measurement and compare your result or numerical result with the parameter. Model-based approaches, analytical and numerical. On the left, you see the definition of analytical model-based approach. So within the analytical model, we have geometry or secret, which means the boundary condition. So the model, analytical model, is built with Maxwell's equations plus the boundary condition. Then you refer to a computer, you can write your computer code, supply user data, and get your numerical result. So in analytical model-based approach, you solve your problem, computer only gives you a result. On the other hand, analytical-based model, you start with Maxwell's equation of boundary conditions. Anybody takes this numerical model, supply the boundary conditions, and then get the numerical result. Discretize your problem, and computer solves it for you for numerical-based approach.
Sir, so sorry for the interruption. Sir, once again, the voice is getting distorted. So, sir, are you using any headset or something like that?
Yes, let me how is it now? Hello?
Yes, sir. Yes, sir, it's audible now. It's clear now.
Okay. Just put the mic to your t-shirt or something.
you hear me now? Hello?
Yes, sir. It's okay now.
Okay. So let me give you a few examples. Now here you see isotropic radiators, either in linear form, planar form, or circular form, and then you change some parameters and get different beams and steer them. On the left, you see a linear array. On the right, you see a circular array with a symmetrical beam. So this is undergraduate students have prepared maybe 15 years ago. And it is an analytical model-based approach because there is only one equation behind this virtual tool, as you see. So everything is solved by yourself, and the graphical user interface gives you fancy results. But this is an analytical model-based approach. Example on two-dimensional propagation scenario. Here you see ray paths through atmosphere. We have a transmit antenna and receive antenna. We have direct rays. The green one, the red one corresponds to diffractions, and blue one corresponds to diffractions, edge or diffractions. Again, this is also analytical model-based approach because write down rays, which means rays from transmit antenna to the receive antenna. You write all the equations of rays for this. Here, the receive antenna is in the shadow region, so you don't have direct ray, but you have reflections and diffractions. So, example 3, this is a numerical-based approach. In the previous one, you use eigenray search. Here, you use ray shooting. And then some of the rays may reach the receive antenna and some may not. So this is a numerical based approach because ray paths are plotted automatically by the program itself. The objective of the ray summation is an analytical based model calculating the contributions of each eigenrays. But ray shooting is a numerical based model which discretize ray paths are plotted by the program. Ray paths, when the medium is inhomogeneous, rays are not straight lines, so vertical refractivity is linear, and you see how rays from the source propagate the range. For example, again, this video shows you non-homogeneous atmosphere. Another example is Parabolic Creation method. And here you deal with two-dimensional Helmholtz wave equation, and you have height and range. So in two dimensions, you have wave propagation in all directions, along height and along the range. But when you do this approximation, when you get rid of fast variations along range, parabolic form, and parabolic form is a one-way forward propagation model. On the other hand, Helmholtz wave equation is wave propagation, forward propagation, and backward reflections. So the of one-way parabolic equation is in terms of Fourier transform FFT. See Fourier transform example. So if you give me on the left vertical profile, I can propagate it step by step to the right, just applying this equation. So give me the full U function, which is vertical profile. I apply a Fourier transform, a multiplication, get the inverse transform, another multiplication, and get the field at the next range step. with all vertical domain. So get this second as the initial field and repeat the procedure until I reach the big C. This is a very nice and effective tool in modeling. Here's an example which is obtained by the package published by IEEE magazine, August 2005. So this one shows you beam effect, sections from that is beam tilt and atmospheric refractivity effects to see how elevated ducts occur range. Fourier transform based parabolic creation is one way model, but you can use the same procedure obtain two-way model. So you can forward propagate and get the reflections and obtain two-way parabolic creation model. To repeat this video, this is a forward propagation. There is an infinite hole here on the right, and then you get the reflections, and you see the appearance of reflections and incident field. Another example, you have infinite reflected wall on the right, and you also have a knife edge obstacle in around 40 kilometers. So you start from the left, go forward, and then you reflect. But because of these obstacles, you have multiple forward and backward reflections, which means resonances occur. So you just repeat the procedure back and forth several times and get the scenario. Another example is FTDT-based time domain propagation. See, time domain propagation of the line source. You have a line source, a rate profile, and then observe how save line source propagate. Okay. So the previous ones are previous results, but these are time domain results. These tools are numerical model-based approaches. Now, we have all those tools, but what about the data we get from those tools? How accurate or how correct are they? The mean of the number given by the computer, that physical result or is that non-physical result? So we need as reference data. One analytical reference model for propagation is integrated with vertical refractivity profile, which causes surface duct equation. So it's the two-dimensional wave equation, it says area equation. And the solution is given by functions with this infinite number of series summation. And the two boundary conditions are at the bottom. SBC means soft boundary conditions. But in electromagnetics, we call it transverse electric case. HBC refers to hard boundary conditions, and it corresponds to transverse magnetic fields. So we have analytical exact solution in terms of function summation. This area function, if negative, we have sine type or cosine type variation. Standing waves, when x is positive, we have exponentially decay events, and x0 corresponds to turning point. The first mode, fifth mode, and 25th mode. So if you add up these modes, represent any type of analytical functions or source function, and then solve the This video shows you 4 different plots. The first one is will give you a mode profile. The second one is the source function, like a Gaussian function, and the last two, the fields at 2 different ranges. To add up mode, first mode, second mode, third mode, and see how to represent second plot. For example, after the 13th or 14th mode, if you add the first 14 every functions can represent its source, then each of the correlation. So summation is nothing but Fourier series of another video. Now here you see the tilt angle. If you have a deep type source, angle 0 degrees, the number of modes that function are drastically increased. For example, if the source has no tilt, only the first 90 for the set of parameters or this set of parameters, but for 10 degrees tilt angle, 8,000. So computation of an exact solution a challenge. If you have an exact solution, it's examples, you compare analytical results with the parabolic creation. Here we have 2 beam type sources, one tilted up, the other one is tilted down, and see how analytical and methods certain ranges and give the strength versus height that has almost perfect agreement on analyticals, parabolic creation, finite element. Once you have your and run many other scenarios, and so calibration is critical in modeling and simulation, and you can find these discussions in our 2017 book. Applied myself. Come to the teaching and training next generations with electromagnetic. What is the behind these? Introduced multi-purpose electromagnetic virtual that can be used in most classical electromagnetic as well as in. We have always looked for something give physical insight and effective so that the young person can intelligent. We need to note that change some parameters, but some other parameters should be so that the user will not get lost in hundreds of parameters. It should be open to non-physical results so that the student may comment on them, may discuss the results. So this is the generic front page, one page scenario. We have geometry parameters, we have boundary conditions, we have source parameters, we have output in graphics form or either inspection windows, and we have command like run, plot, and exit. This is the generic form, and these are some of the that we have published for the last 50 years or so. These are ones that can be used 10% propagation. These are for guided way theory, undergraduate level or graduate level. These are some of them that can be used in scattering and diffraction. I already give you examples about propagation and antenna. So let me give you examples of virtual tools, RCS and diffraction. This is an RCS in three-dimensional domain. On the left top, an airplane. On the right top, you see its graphics file in 3D format. At the bottom, it's discrete FDD and command models. So the top pictures are created automatically program itself from given graphics file. And then you run and your capture of transient time domain fields. So you have a plane wave of pulse time, hit the object and see the electromagnetic effects around this object. So it happens only in a few nanoseconds perhaps. You record its transient times and you do effect and get the another two videos with one F-16 on the right, F-16 side by side on the left. So you can record them and see how electromagnetic interact and then get the results. So in RCS modeling, you run the FDD, then run Fourier transform and plot RCS versus angle or RCS versus time. These virtual tools are good not only for teaching but also. So as I said before, we can play what if type games. What if F-16 one on top of the other or side by side? F-16 get a result like this one, for example. You see RCS versus frequency. Red one comes to one F-16, blue one corresponds to two F-16. The scenario polarization also shown on this figure. So this is critical. At some frequencies, two F-16 backscatter RCS lower than one F-16. So two F-16 may be less visible than one F-16, but at other frequencies, F-16 may be more visible on radar than one F-16. So RCS is very critical and very complex. So you cannot predict, for example, from low frequency behaviors, high frequency. So you repeat your calculation or your measurement at every single. Examples are diffraction theory. As we said before, electromagnetic waves interact with objects and scatter. And the word scattering reflections, and diffractions. And tips cause diffraction. So here you see reflection, multiple reflections on the left of this triangular object, but on the right. So edges and tips act as secondary sources. So here you see electromagnetic plane wave interacting with perfect electric strip. You see the total fields. Now this is only the scattered fields. Here you see the total fields for different angle of rotation. And when you remove the incident field, you get the scattered field. Videos showing scattered fields at the same time. Include incident field and scattered fields. Scattered field is equal to total field minus incident field. You can play type games with different boundary conditions and observe how electromagnetic waves. This is our recent electromagnetic package. It is used for diffraction on analytical models as well as models. So we combine high frequency asymptotics like FTD and objects. Fields around the wedge, soft part left, hard part the right of the line source. Here you see total fields on the left and only diffracted fields on the right. So if you subtract the incident and reflected fields from the total fields, you get the difference. Single reflection, total fields. Our last book will appear in 2 weeks, have 2 or 3 months delay. Title will be Production Modeling and Simulation of that. Now, the conclusions. Wave-oriented electromagnetic engineering is an effective way of identifying both technical and educational challenges. Computer capabilities has revolutionized the analysis of modeling and simulation. To understand physics behind mathematics before using and results with experiments. Keep in mind the assumptions and probability. Look at the object as a whole.
Excuse me, sir. Hello, sir. Your voice is breaking, sir.
Excuse me?
Hello, sir. Your voice is breaking. Can you speak a little louder, please?
Hello?
Yes, sir. Yes, sir. Now it's okay.
Okay. So multiphysics has also become essential, so you need to establish disciplinary collaborations. New approaches such as virtual reality or artificial intelligence are very attractive for the engineers. Mass education. So basic lectures such as measurement should be renewed accordingly. Training with these electromagnetic virtual tools is highly effective. Can let the students play with these tools. They let them visualize electromagnetic wave object interaction of the given scenarios and then create their own scenarios. They then start electromagnetic play with Maxwell's equations. So visualization first and then mathematics. This will establish well understanding between mathematics. Students who are further interested in electromagnetics get the supply source codes and modify, develop better ones. Now, these are critical. Today's engineering students are very lucky. There are excellent commercial packages and measurement devices. Today's engineers are very unlucky because there are excellent commercial packages and measurement devices. So we have advantages and disadvantages of having commercial packages and highly sophisticated measurement devices. Words in our first book, we use the motto, let's do it. The second one, we use the motto, yes, you can. Are the IEEE mottos, tell me, I'll forget, show me, I'll remember, involve me, I'll understand. And thank you.
Thank you, sir. Thank you, sir, for your excellent presentation. Now may I request Siddiqui sir to say a few words.
Hello?
Hello, Siddiqui sir.
Yeah, I try to see.
Jawad sir, Jawad sir. Saha sir, is Jawad sir there?
You may first take up the Q&A. After that, we can check them.
So, sir, there are few questions from our participants. One question is, what are the main differences between geometric optics and physical optics approaches? What criteria can be used to select these approaches for analysis?
Now, as I said before, geometric optics uses Snell's law. So you just plot the ray paths and write down their equations, mathematical equations. So if you can plot the ray paths, then geometric optics is easy to apply. But for the physical optics, you need to solve the differential equation given for scattering or diffraction. But the results are more meaningful in physical optics. So geometric optics gives you the solution only in illuminated sites, which means when the source is is not in the shadow region. So if the source is in the shadow region, or if the observer is in the shadow region, and if you still want to use geometric optics, you need to include GTD, geometrical theory of diffraction. But GTD suffers in critical regions like caustics or shadow boundary or incident boundary. So the deficiency of GTD was removed by UTD. But on the other hand, physical optics and physical theory of diffraction are more general and more dependable. So it depends on the geometry of the problem. You can use either of them, GO or PO, with GTD or PT.
Hello, sir.
Yeah.
Yeah, sir. Now we are proceeding with the question answer session, right? Hello?
Yep. I'm listening.
Am I audible?
Yes. Hello.
Hello, sir. I think we have answered that question. Now coming back to the, you have given that. Now coming back again, while computing the RCS, sir, am I audible? Sir, while computing the RCS, which region has to be considered? What is your comment in if computation has to be performed in the Rayleigh or optical region, as scattering will be different?
You repeat the question, please.
Yes, sir. I will repeat. While computing the RCS, which region has to be considered? What is your comment if the computation has been performed in Rayleigh or optical region, as the scattering will be different?
It depends on your problem. For example, if you have 16 target, like a 15 or 20 meter aircraft, and if you have a radar which operates at 1 gigahertz to 20 gigahertz, then the RCS region, optical region, because the wavelength of the radar signal is very low, small compared to the target. If you have a high frequency radar which operates at 20 megahertz or 5 megahertz, then the RCS region resonance. So it depends on radar and the dimension of the target.
Sir, next question is by Swapnil Gaul. Hello, Swapnil Gaul. If you are there, you can directly ask the question with Sevgi, sir. Swapnil Gaul, are you there? Mr. Swapnil Gaul?
Yes, sir. So, sir, my question is that, am I audible? Just a moment. Am I audible, sir?
May I suggest to keep yourself muted if you are not speaking?
Okay. I think I'm audible now.
Yes.
Okay. Sir, when we are like using coating on a particular material like object, whether it is like small paint or something, multi-layer composite like that. So in physical optics, we can take care of all the triangle or facet at the same time. But while using FDTD, how we are going to model that particular coating means when we mesh across a cross section or thickness, then it will cost a lot of element size, and mesh size will be very small, and it will be like computationally too much burden to solve.
It's actually FDDT with very tiny coating, material coating.
Yes.
Is insufficient. So
okay.
If you want to use FDDT alone, you need subgridding. So you can use different grid sizes near the or under coating and elsewhere. Okay. One approach is to use multi-gridding approach. The other one is to use FDDT with high frequency asymptotics or method of moments in hybrid form.
Okay, so there will be like some formulation, analytical formulation also.
Yeah, there is no direct and simple way of dealing with
coated object.
Coating.
Okay, and sir, many times that I had faced with a few problems which are having like very small diameter wires, and we want to solve that particular problem with physical optics. And in physical optics, it is preferred that triafacet will be there, but in small wire, small diameter wire, like 1D element, how we are going to treat that? We use the MOM for that, but MOM is costing a lot of element size if the wire is very large, means in the length. So MOM is like preferred, and we are using that. But if you want to like use PO for that case, then how we can proceed?
Again, can combine PO and PTD with method of moments in hybrid form, but I don't have direct answer now because very infinitely thin wires, their numerical implementation are really complex and difficult.
Okay, so the best solution is to find out some analytical way and to model that particular segment.
Yes, whenever you are stuck, you try to use analytical approaches first because they are easy to use.
Yes, sir. So it will be like combination of both.
Yes, yes. So you need to combine analytical methods with the numerical ones, but try to stick with the analytical approaches as far as possible. So try to proceed with the analytical representations and derivations as far as possible, and then go to the numerical domain.
Yes, sir. Because sir, in existing softwares also like don't solve these kind of problems in that way, like very small diameter thickness with PO like that.
Yeah, thanks,
Okay.
Shamil, for
Yeah. Thank you,
introduction.
sir.
Yeah. Okay, good. Anu, take care of the next part.
All the queries are answered, sir. Almost all the queries. If any speakers are left, they can directly ask with Sevgi, sir. If any speaker wants to ask their question, they can directly ask.
Now, for the students and for the young researchers, you have my email addresses. So send me emails whenever you want. I'll be able to reply them. I'll be happy to reply them. Okay.
Thank you very much, sir. Thank you. Sir, Jawad sir is there. Say a few words.
I think we are all set.
So, are you there, Professor Siddiqui? Are you there?
Yes. I
Yeah,
just
please.
had to. I had this thing muted.
Your
Yeah.
felicitation for today's talk and in general. Yeah,
Yes,
please.
thank you so much. I was looking forward to this talk because I missed Dr. Segbe's talk in CAP when he was there in 2018 for the keynote address, and we had a discussion like in Egypt. Like I wanted him to be in India because I'm really I was looking forward to this talk because I feel that we are too much dependent on the softwares without understanding the underlying phenomena, because the computational electromagnetics is such an integral part of understanding electromagnetics and understanding the physical aspects of this the electromagnetic theory. But however, most of our students are exposed to software directly. They get the results, and without even understanding, probably the misinterpretation happens, and that it doesn't augur well for the students, for the development, because eventually they are going to be the leaders and teachers. So this legacy, has to change, and I know Turkey has gone a long way. They have a legacy in this competition electromagnetics, and Dr. Sevgi have been a path leader in that aspect. So I'm glad, and thank you for this talk, and I'm hopeful and that there are people who takes the important aspects of this talk and move forward. I know Swapnil Goel has been doing a lot of good work in this domain in India, and as academicians, I would request with Chinmay, we had a discussion with Chinmay and other academicians too, that to give an importance to this aspect of computational electromagnetics and expose the students in this domain a bit more than what we have been doing last few years. So thank you so much. It was great having you, Dr. Sevgi, and stay safe. Thank you so much for accepting this, our invitation. And it was nice to see you here. Thank you.
See you. Yeah.
Thank you, sir. Thank you, Dr. Javad Siddiqui, sir. It's a pleasure that you were able to spare time to join with us today. Now, I would like to call our event host, Meher and Malavika, to continue with the session. So, Meher and Malavika, are you there?
Am I audible?
Yeah, you are audible. You will just continue with you just continue the session. I think the next speaker.
So next I would like to invite Mr. Dr. Devdeep Sarkar from Indian Institute of Science, Bangalore, to say a few words.
So good evening, everyone. I hope I am audible. So,
Yes, sir, you are audible.
Yeah. So
Yes,
first
sir,
of all,
you're audible.
Yeah, I'd like to thank Professor Sevgi for such an informative talk. And I think he has covered all the various like computational tools that are and mechanisms that are used for various solving various electromagnetic problems, as well as he has emphasized upon the use of these softwares to enhance the knowledge of students and try to interpret the like it can probably bridge the gap between the mathematics part and the actual physical phenomena, and through the visualization the students can understand what is actually happening, because most often undergrad students just by looking at the math they sometimes get too much intimidated. And I think this kind of tools, and I really like the last part of his talk where he was showing these various interactions of electromagnetic waves with the edges and these small wires. And so I think, yeah, it was very informative for me also. Maybe I'll contact him later on personally to learn and discuss a few things from him. So, and I would also like to thank the APS student branch chapters and the AP Society Kerala chapter for organizing this deal. So I hope that such events continue in future, and we are the community, electromagnetic community as a whole, gets benefited from that. So with that, I will not take much time. So thank you once again, Professor Sevgi and IEEE.
Thank you, sir. Thank you, Javed, sir. It was a great session indeed. Now I would like to call our member, APS member of the CB Barton Hill, to give the vote of thanks with this concluding the event. I request Mahar Malavika to give the vote of thanks.
Before that, is Arijit there? Arijit Mitra?
Yes. Now I would like Dr.
Anu?
Arjit Mitra to say the formal words of thanks.
Sir, Arjit is there.
Yeah, good evening.
Yeah.
So, yeah, so very good evening to everyone. On behalf of APS and MPTS Kerala chapter, I'd like to thank Professor Levent Sevgi for his very interesting talk, I must say, today. We are really grateful to have him for the talk today, for accepting our invitation and taking time out of his very busy schedule for this distinguished lecture. I'm sure all the participants will be immensely benefited from this session. Thank you once again, sir. I would also like to thank the APS Student Branch Chapter GEC Button Hill under the able leadership of Professor Anu Mohammed for taking this initiative of APS Distinguished Lecture Series. I thank and congratulate all the student volunteers who have put together the relentless effort for organizing today's event, and wish them good luck for their future events also. We are also extremely honored to have with us Dr. Imran Shah, who is the MPTS Kerala Chair and former APS Kerala Chair. We thank him for his continuous guidance, leadership, and to especially mention his visionary approach towards our chapter activities. I also thank the other APS and MPTS Kerala office bearers for their dedicated service and support. Lastly, I thank all the participants from across academia industry for today. Thank you for your participation, and I hope to see you in your future events also. With this, I conclude. Thank you once again to everyone.
Excuse me, Swapnil, we want Swapnil and my student members, we should take a group photo because we have to.
Yes, sir. I was going to say that, sir. Yes, sir. I request everyone, all the participants, APS members, XCOM members, MPTS members to please turn on their mics. Not mics, to turn on their videos so we can take a group photo. I request everyone to just.
You are looking good. You don't have to set your hair, Sapnil, again and again. You are looking good.
Okay, sir. Okay. So, yes, sir. So, Shivada, can you just take the pic?
Sure, Swapnil.
Yeah. I see we have people from all across the world. Shivada, Akshay, you will also take this.
Yeah. Let us know when it is done.
Shivada, Are you done with the photo?
Yeah. Yes, Swapnil.
Okay. Yeah, I think this concludes our event for today. It was a great event. And at last, also, I'd like to thank Dr. Sevgi sir for taking time and coming here. I hope you would come again to our college by this virtual means, or if this corona pandemic goes away, a session at our college someday. And so, thanking all, signing off from maybe APS GCB Barton Hill. Thank you.
Thank you. Bye bye. Take care.
Bye. Bye. Thank you, Professor Segbe. Bye.
Bye, sir.